Het is hem absoluut al onder de rode.
Okay. Okay, today's my talk is low power is always the right way. A little strange title, but this is my policy to develop ADC or some chips. This is through my experience in the development of the AD converters. So the aim of this talk is show how to drastically reduce the power consumption of ADC. How? Next is how low power ADC contributes to create new electric system. Lastly, show the fundamental development work for low power ADC is to increase the accuracy even if using large mismatch small devices and how cut off the static current. So this is the contents of my talk. First topic is CMOS two-step ADC are using capacitive interpolation for digital handy camcorder. In technical aspect, this is a very memorial ADC. This is because technology of the ADC is completely changed from the bipolar to CMOS. Next is 7-bit 400 MHz ADC using gate-weighted interpolation and mixed signal SoC for DVD system. And in terms of the circuit technology, this shows such the static current and the circuit to semi-dynamic current circuit. And next is 100 gigasample per second interleaved ADC for optical communication systems and techniques for low energy conversion in spite of operation sampling frequencies such as extremely high of 100 gigasample per second. So current ADC use full dynamic analog circuit, no static current flows. And lastly, I would like to introduce you recent my work, such as charge-based mixed signal mark circuit for high energy efficiency and neural computers. In a technical aspect, this is from current-based or resistor-based circuit to charge or capacitive-based circuit. First is CMOS two-step ADC. The motivation is around 1990. I was technical staff in Panasonic. So Panasonic developed the handy camera recorder using firstly use of digital signal processing. The motivation is to stabilize the image caused by the camera shake by detecting the motion vector and compensate it by controlling the image memory address. Okay, so low power video rate CMOS ADC was required to realize such a digital processing system. So The aim of why the CMOS ADC is needed. One great motivation is to realize a one-chip solution, such as this is a video rate ADC, and this is the digital video filters, and this is such as 8-bit CPU. CMOS ADC was strongly required, but at around 1990, the power consumption of CMOS ADC is this red circle, and bipolar and bi-CMOS ADC, and this blue box. In terms of the power consumption, and bipolar and CMOS ADC is competed. In power in around 1990, so we succeeded. Very low power CMOS ADC, the power is about 1/8 to others. So after that, all the ADC technology changed from the bipolar to CMOS. This is a very memorial ADC. So at that moment, the bipolar still used for the ADC. Why? One is mismatch. This is offset voltage or mismatch voltage. This is analog bipolar. Can realize 10-bit ADC. However, the MOS is 2 times larger. And large size is needed to reduce the mismatch. This is nature, very fundamental nature of the CMOS. This is mismatch voltage, and this is gate area. So if we use small gate area to reduce the power, this results in the increase of the mismatch. Sometimes we need to increase the gate area. This results in increase of the power. The mismatch of the CMOS transistor basically become larger with reducing the size. This is another fact. This is the area, and this is conversion energy. And this plot is area versus energy for published 5-bit and 6-bit CMOS ADC. As you can see, the large area results in large energy. So if we want to realize low energy, low power ADC, we should reduce transistor size. So, but the issue is if this is a transistor size, and of course, and larger transistor size result in increase of operating energy. So this is very bad. So if we use more smaller size, this increase the mismatch. How to address this serious issue is the main theme for developing the ADC. So at that moment, at that moment, CMOS comparator shows much power, and this is to address this issue to increasing the size and to reduce mismatch. However, the resolution is at most 6 feet or 7 feet. So I changed the idea of for the CMOS comparator. We used this chopper inverter comparator, very simple. This and switch capacitor. So firstly, and found this shorten this node. This acts as a diode, and this is the capacitor. So capacitor sampling the signal and also the fluctuation of mismatch of the transistor. This is phase one, the signal tracking and absorb the mismatch. Next is the phase one. In phase one and phase two, switch is selected to V reference, and this switch is open. So this inverter acts as an amplifier. So this action realize the sample and hold and compare the V signal and V reference and this capacitive coupling. Of course, mismatch can be cancelled. So, using this analog technique, the small size of large mismatch is acceptable. So, even though use the small size from transistor, we can realize more higher bit, such as 9 bit APC, and we can realize. So, next technique to reduce the power is architectural design. At that moment, the front edge is to realize the bigger. However, the issue is the number of the operator is too. So for the technique to the large area power consumption. So every engineer try to use such as ADC and fastly and coarse ADC determine the signal level. And next, fine ADC works and determine the signal in more fine information. So using this two-step method, the number of the operator can be reduced by 64. Compared with this number, 60 and 16th of the area can be expected. But issue is the required small mismatch between the two conversion lanes. This is some example. This is the course conversion range and this is conversion range. So there is between the two conversion range, large differential nonlinearity error, nonlinearity error occurs. Maybe this is developed at around 1990. So the method is not mature. So we created this interpolation method. Interpolation method is select the two signals, and amplify. So this is output of the amplifier. So this is the register. So register is divided between the voltage. So this forms the intermediate voltage. Okay, using this method, this is the interpolation. This after some connection of the in terms of the differential nonlinearity error, it's okay, more smooth compared with this fixed value. So this is interpolation. So this is the mathematical expression of the interpolation. The sum of two squares. This is another signal. If we obtain this position, we can realize such related data, so makes the internal division. So conventionally, the ABC is difference, voltage difference to make the signal like still. However, in the convention, no need of some explicit reference voltage, just using rate and sound. So um, previously, we developed this method for the interpolation. However, not be can be applied to CMOS. Is such a flash and using chopper. So we uh, realized interpolation using a capacitive method, such a connected to voltage with a capacitor, and also connected to voltage next stage by a capacitor. So we can realize capacitive interpolation. By using the method, that we can decimate this inverter. We can reduce the power. And also this connection of the two voltage after the spring coil network very smooth the conversion. So to realize this pipeline operation is needed. Such voltage is stored here. And the next is open here, open the switch and close here and generates voltage. And this voltage is expressed this formula. This means interpolation can be realized. So by using the techniques such as use of chopper CMOS comparator and using chemistry interpolation, we can realize video rate and CMOS EDC. This is our development EDC this area. Converged energy published here. And currently, to express performance of the ADC, we use conversion. However, this is the first um, articles, 3 times in San Francisco, shows how this ADC can reduce power on the. So this is the first use of such an energy as a performance. And to the success of this ultra low power CMOS ADC triggers the emergence of low power electronics. Low power electronics becomes a major stream of IC, of course. However, at that moment, such as 1994 or 1995, almost no US engineer, pay attention to the low power electronics. They paid attention only for the high speed, high performance. Power is not an issue. Like this. This is because at that moment, in US, there is no consumer electronic maker, just military maker. Some military makers, such as military maker, or the IBM, something, and also yeah, and the TRW, for example, Benjamin. So no concern about the power. So I organized the world first and and much low electronics. Opa is very popular now, but at that moment, it is not popular. And this is how the handy type, research type, and so this is one example for the how low power is important to create a new product. And, low power DSP is embedded to DC-DC. This is DSP core. This is DC-DC. So the system is determining lowest and operating voltage to operate enough power, can reduce power by adjusting the supply voltage that is reflected by some needed operation speed. So we introduced this local is embedded on chip DC-DC. So using this DC local DSP, we developed this torch type. It is it was used for internal wireless communication in Nagano Winter Olympics Game 1998. So this maybe the first research type and the zero phone. So low power consumption is very important. Here is such a small factor system such as portable and also somewhat wearable system or implantable system. And other interesting, I was invited to the IETM 2003 to discuss how to solve the power crisis of the CPU panels. This is because at that moment, power consumption of Pentium processor has reached 100 watt. And facing the power crisis at around 2003, CPU has changed the design from increasing the clock frequencies. This is a fundamental strategy of the Intel. And change to the multi-core strategy, limit the highest clock frequency and increasing the number of the core. This is after the power crisis. So as a panel discussion, I showed this figure and emphasize the CPU consumer can reduce the power 10 times lower. This is such 100 MIPS, 1000 MIPS. This is the power. So this is such a Pentium CPU, PC or memory. This is the embedded CPU, Panasonic level. The 10 times lower power, even though performance is same. So Intel should pay much attention to the low power consumption and change technology to the multi-core. Next is 7-bit and 400 mega ADC. This is the DVD system. This is a DVD recorder. You can see this is a big crowd. This means the error, large error due to the low SNR. So high-speed DSP is required for the, such as filter, ADC equalizer, and also error correction. So this DSP technology should be applied to the DSP. So after that, the we can get a more clear, so error-free signal. And the issue is always the ADC, and that means 7,400 mega sample ADC, even though it's in consumer. This is because it is not easy. For example, saying such a 6-bit 1 giga ADC, we developed but consume to and we published 6-bit 800 megahertz ADC. This is the world first in 2000. But our consumption is 400 milliwatt, too large. So we need a more low power ADC, such as less than 50 milliwatt. And we can realize this ADC consumes 500 milliwatt, 0.18 microsieverts. So this is conversion frequency. This is normalized conversion energy. So we developed 10 times lower ADC compared to others. How to realize? This is a chip of the ADC. And I am using the interpolated method. This is a flash ADC, and this is large, and this is free amplifier. So in the interpolated flash ADC, and we skip this and connect between the two amplifier using the register, series of the register. So using this method, we estimate this error distribution, and only voltage is created by the interpolation method. So by using this interpolation, this offset can be reduced effectively as the interpolation. So this can improve the linear. So again, we show here, but the issue is use of the register. Register itself consumes power. So how to avoid this register is essential work for the global ADC design. So we introduce this pair of transistor that works in triode, which is programmed. So by using the method, this transistor register is inserted to the differential CMOS flow. So no constant current flows. However, this circuit can realize this is a conductance and such as differential conductance and form interpolation. So this is no need of the register, power consumed register, just connect with the gate. So we can realize very high speed with low power ADC, and we can embed it into SoC for the DVD. All the DVD system can be integrated on one single SoC. This SoC contains many CPU and DSP, many processor, pixel processor, hardware processor, for example. So it can be integrated can integrate also ADC. So after the ADC and the DVD system become very small and very simple local. So we can now use DVD laptop computer. This can this contribute to reduce the form factor of the DVD. So next topic is side for optical communication. One serious issue of the cable communication, electric loss is increased by increased frequency. So due to this effect, the waveform of the RX is high, doesn't open. So we can open the eye by using DSP. Yes. So one way is using this DSP, such a recovered, this is a recovered data, for searching similar bit sequence data. And the other is using the optical communication. Conventional use the optical communication is such as on or off in the very high speed, on, off, on, off, off. But due to the dispersion effect in optical fiber, so this operation can be is degraded by using this dispersion effect in the fiber. So DSP compensate this such a shift, and this is such a RX signal. This is a TX signal. This is the RX signal. So we should separate it. So DSP can separate like this. So we can realize high data optical communication. But not only develop such a high speed DSP, also such a very high speed ADSP, second, extremely high speed. So to realize this high speed ADC, conventionally interleaving psi ADC is used. This is 128 psi ADC works as interleaved manner. So finally realize 100 gigasample per second. So each psi ADC is very small and this is very simple. And psi ADC is simple, small, and global. And also important things, it can receive the full benefit of the technology scaling. So and the interleaved psi ADC can realize about 100 gigasample per second for the wireless, wire communication. So this is the energy consumption of psi ADC, 10 bit ADC. Amazingly, and the psi ADC power energy is 1,000 and lower during only 12 years. So fine. One important point is this, such as conventional science and consumes current science use only capacitor and switch and the controller logic. So no power consumption, no power consumption. And logic, this is the CMOS logic. And this can be faster and lower by technology scaling. So this is my idea. So the basic concept of low power ADC. And this is a conventional using a constant current, like the CMOS, CML, current mode logic, amplifier. The issue is to increase the frequency, operating frequency, we should increase the power. So increase the static current is required for increasing the operation speed. This is the CMOS. CMOS energy dissipation just C square only. So even though we uh, increase the speed by decrease the distance, the energy dissipation is same. So no increase of the consumed energy if speed is up by decreasing the resistance. So ADC after the CMOS logic is the key to realize low energy at the high speed. But one point is use of small use of the capacitance, not only the sample and hold, but also such as using the split capacitor can realize such as difference change. But the issue of the side DC comparator, conventional comparator and use such as however, the issue is somehow the noise. So resolution is basically a 10-bit level. However, we suppress the noise 10 times, 9 times more compared with conventional one by using this distance. So we can realize 12-bit AC. Also, important is dynamic amplifier. Dynamic amplifier is only the capacitor, not the resistor. But even though no use of a resistor, we can realize the amplifier function. Multiplication function. So no static current flows, but can realize some gain, such as 6 times. This is suitable for this is a low energy ADC as already. So other technique is how to suppress mismatch without any power consumption. In this case, combined with the dynamic amplifier, so change this to control the circuit. That result in control of mismatch. So this is a major factor. So where without calibration, offset calibration, takes much the mismatch 30 millivolt. But by using this offset calibration, we can suppress such as 3 millivolt. So this is one technique. Even who use such a large mismatch transistor, this mismatch, this method with so charge base, the MS mark and the button time is reaching. So we have the age from digital computer to other computer such as AI or quantum computer. So we now developing the charge base and MS mark composed with and side. Uh, using a very small energy side DC, such as 8 and also very small size and capacitive die, the size is only 3 micron by 1 micron for the C. We can realize a very high energy efficiency, such as 200 with area of 0.1, sorry, 1.1%, high speed population of 180 megahertz. This the charge-based mark the reduced to 175 and reduced the area to 122 compared with such a 8-bit digital mark. So by using a method and we can obtain the maybe we can realize such a very energy efficiency such as 450 if we use 16 nanometer chip, this is energy is very scalable with technology scale. So in future, we would like to combine this method with such a converter, such advanced this is external map in near memory computing. So in conclusion, power reduction is always effective to reduce and cost and size and realize longer power reduction also opens the door for new electric systems, portable system, the wearable system, and portable system. Low power EDC has been always requested for new system. A small size device are equivalent for low power and high speed operation. However, the increased mismatch and decrease the accuracy. So, so such as cutoff, static current flow, and full receiving technology scaling, and mismatch utilization, interpolation architecture, and also lastly, I don't important importance is how to use this other method to the computer. So I here high energy efficiency for processing. Thank you very much.
Some of you, some? No, yes?
Thank you very much for the very interesting, great overview. Progress. Question and a very technical one. Do you think that we arrive to a limit for the power reduction? I mean that every time we define 10 by 20, I think so there are limits to that. And my second part is what should we work on for low power architecture or technology?
Question. I shows architecture for such a ADC needed to acquire the benefit of technology scale. So conventionally analog engineer sometimes ignore the effect of the technology scale. So for the rest of the shows the how friendly with the technology is very important to reduce. This is because, for example, now my company designs some system or optical system by using 16 nanometer CMOS FinFET or 12 nanometer. But so for 5G system requires the filter. So filter frequency is maybe on 16. So from 5 megahertz to 200 megahertz, 16 bucks. So this means we need opium. But opium is not opium design with 0.8 volt or almost no voltage. So we increase operating voltage up to 1 volt. 1 volt is some sort of limitation of operation of the opium. So how to reduce need of the opium is very key. This is because when we use such an opium method, we cannot use the advanced sequence. So we cannot obtain the benefit of the technology speed. So for the such analog engineer, maybe I think the design of the opium is so comparator base is such as SADC can operate such as 0.6. This is because that no need of just such a comparator with such a 0.6 volt. So for the high speed and low energy system, such as selection technology and selection of the architecture, selection of the circuit is a very important. So,
thank you very much for the presentation. I'm wondering, sometimes when I design a low power systems, the power of the ABC part is
always. So
always trouble me because the power, the sensor has very, and basically the sensor has maybe sometimes only less than 1 million volts. But the ADC part always consume 10 or 100 millivolts. So we are also wondering, is ADC friendly for the consumer consuming electronics products?
okay. Yeah, ADC. Power consumption of the ADC drastically reduced. So compared with the previous technique, current ADC reduced the power so much. However, the issue is this is such as 10-bit ADC. It's okay. However, such as 14-bit ADC consume much power. Yeah. So this is one nature of the circuit, such as power is limited by the capacitor, such as the KT over C. In this case, such as higher resolution requires large capacitor and result in large power. So, system designer must select the ADC resolution small as possible. But such as a combination with such a one case is even though you use such a 10-bit ADC, you can realize effectively 40-bit by using such a variable gain amplifier or some use of delta sigma processing method. So, basically, such as high resolution and high speed ADC consumes much power. That is the nature. Okay.
We trying to design the system. We just get some data from the sensors, the analog data, and we sample such data by the digital. So there is no say the power lower.
Yeah, such a system design is very important, and such as sensor and the ADC and the DSP. Sometimes such as amplifier, tone with amplifier, sometimes. So as a combination is very important to totally we can reduce. So that is some works for some system design.
Any other question? Yeah, I have one. You talked about the consumption about doing analog to digital conversion and like that. Do you think that you consume less if we only treat analog signals with analog computing and vice versa, digital signals with digital computing, or is this impossible?
It's impossible.
アナログコンピューティング、アナログ追加だけ、データコンピューティングと一緒、データを追加だけと、
Signal and
this level is possible compared to AD and mixing. But processing. The analog signal is processed by analog processor. Analog signal is processed by data.
That is one idea, recent idea. So, yes, for example, digital circuit requires a more fine process, so such as 3 nanometer or 2 nanometer. However, for the analog, no need, or sometimes cannot use. So in this case, one idea is such a chiplet method. Chiplet. So analog is such a use such a analog dedicated to analog suitable process and combine with some assemble technique such as stack. So that is really needed. Sometimes similar to the situation with memory and the memory no need of such a fine scaled device compared with such a logic circuit. So recently such a processor stuck the memory. For example, one example is famous NVIDIA. Okay.
Okay, well, thank you again.